Good day, viewers. You're welcome to Science Spectrum with Dawn. In today's class, or today's discourse, in Physics Classic, I'll be talking about measuring instruments for barometric or atmospheric pressure. So I'll talk on measuring instruments. Measuring instruments of barometric pressure. All right, and of course, what are these instruments? For my convenience, there are namely two. The first one is what I call a barometer, and of course the second is a YouTube manometer, so it's a manometer. So this instrument does measure the barometric or the atmospheric pressure. So let me start with the barometer like so. Now, this experiment was done in 1643 by Evangelista Torricelli. Now, what did he do? How was he able to figure out the barometric pressure? Now, this was what he did. So there are two approaches to this. The first approach would be by Torricelli, and of course the second is still Torricelli, but it will be in the reverse perspective. Now, so what did he do? He had the reservoir like so, where he poured mercury on. So this is a reservoir. And then mercury is filled to the brim, like so. So let the mercury level be this, so to speak. Alright. So what he did was he got a glass tube that is sealed at the top. So this is a glass tube that is sealed at the top. Now, I want you to appreciate something. If this glass tube hadn't been sealed at the top, if it's submerged in this reservoir, right? So what you see is that the level of mercury in the glass tube and outside of the tube would agree on the same level. Now, this glass tube is sealed. It's sealed like so at the tip. So he took the glass tube and poured mercury on it. So this glass tube was filled with mercury. So this is now filled with mercury and now dipped inside the reservoir. So what you see is this. This is the glass tube now. It has been filled with mercury. Now, so to know what the barometric pressure is, if you lift this glass tube up a little, you lift it up a little, now you get pressure difference. So this mercury in this tube, it starts to break loose. So once you lift it up a little, and it gets to this, so once you're lifting it up, it breaks loose. Let's say, and stops. Why does it stop? It stops because that the atmospheric pressure here that acts on the surface of this reservoir can actually sustain this column of mercury, which are represented by H. So the atmospheric pressure can sustain this column. In other words, the pressure right at the surface and the pressure in this glass And the height of the mercury that the atmospheric pressure can sustain is exactly that value is exactly 760 millimeter. And of course in meter, this is 0.76 meter. So what it means is that 1 atmosphere, which would be the pressure we should get here now, this is times the height is 0.76. So when you solve this, you find out that the pressure right here, the pressure is roughly the atmospheric pressure, which is 1.03 times 10 to the power 5 Pascal. So you could just ignore this number and let me just use 10 to the power 5 Pascal. So it's comparable to the atmospheric pressure. So 1 atmosphere is in Pascal 1.013 times 10 to the power 5 Pascal. And of course it's equivalent to 760 torricelli or millimeter of mercury. And of course, English units, force is in pounds, is measured in pounds, and area is in square inches. So this would be 14.7 pounds per square inch. So we call this PSI, 14.7 PSI. These are equivalent statements of what 1 atmosphere produces. Now, so this term is exactly what you see right here. Now, this instrument is exactly telling you that the pressure right here at the surface of the liquid is 1 atmosphere. So what it means is 1 atmosphere is exactly the pressure that 760 millimeters of mercury in the glass would exert on this surface of the reservoir. That's how, and of course at a temperature of 0 degrees Celsius, that's how this works. So if I tell you that, so for different columns of this mercury, you could tell what the pressure is. Because 760 millimeters of mercury is exactly 1 atmosphere, which is this value. So let's say, for example, if it drops to 720, you could actually tell what the pressure is right now. So let me just give an instance. So let's take, for example, let's say, if the pressure, let's say the pressure drops to, let's say 700, let's say this column drops to 700, take it for instance, that is what was observed. Now, what would be its equivalent in atmosphere? Now we do know that 760 millimeter of mercury, it is mercury, the same, translates to 1 atmosphere. So if I lose this, I lose 1 zero. So what you're left with is 70 divided by 76, and the unit here is atmosphere. And of course, 70 divided by 76 turns out to be, let's say, roughly 0.92 atmosphere. And you convert this to Pascal. How? You know that 1 atmosphere pressure is equivalent to 1.013 times 10 to the power 5 Pascal. So when I lose the atmosphere here, then anytime you get when you multiply what gives you the answer. So it's just as good as saying 1, 2, 1, 2, 3, 1, 2. So it's just as good as saying 0.92 or 92 times 1013. 92 times 1013. And that's exactly 93196 Pascal. That is what this column, if it's going to be 700, translates to. Now, so this is the first approach. The second approach now will be this. You want to do this for a while, and if you're watching, you will screenshot it. So I'm going to play this one. Alright. So now we have a second approach for measuring barometric pressure. And the second approach is pretty straightforward. It's still barometric pressure. So you have a reservoir like so, like we had earlier. turns out to be that the level of mercury starts to break loose. So you see the mercury starts coming downwards. But that height exactly, this height at which the level of the mercury starts to break loose, represented by H, is exactly a column of mercury that defines what's one atmosphere. So it means the atmospheric pressure here and the atmospheric pressure here can sustain this column. And this column is exactly 760 millimeter. And of course, this is the same as 0.76. So this is how barometric pressure is measured. So you see the same formula. The pressure density is empty and it's closed off. The pressure at the top is zero. So to get the pressure here, at the bottom, let's say this is point B, it will be the pressure at the top plus the density of mercury, which we talked about earlier, times G times H, rho GH. Now clearly, we did that earlier. Let's say the answer is roughly 10 raised to the power 5 Pascal, and that is exactly 1 atmosphere. Now, I could also use a different liquid other than mercury to do this. So let's say, for instance, what if I decide to use, let me say I used water or even oil. Let me say I used oil. Take for instance, let's say I used oil. Oil. The oil is way less dense than mercury and even less dense than water. So let me just say, for example, let me just use water. So let's say I use water. And the density of water is 1,000 kilograms per cubic meter. Now, at what height will this column of mercury break loose? At what height can the atmospheric pressure be able to sustain the height of the water? Now we'll check that out. It is exactly, you just defined the reference density, which is mercury. See how it was to regenerate. You divide that by the density of water. You multiply this by the reference height for the mercury, that's 0.76 meter. And of course, mercury is 13,600 kilograms per cubic meter. Water is 1,000 kilograms per cubic meter. Multiply it by 0.76 meter. So it turns out to be this. I do the unit here. So it turns out to be that this is exactly 13.6. No? Yeah, 13.6 right here. This is 13.6 times 0.76 meter. So this is roughly 10 meter. So that's the height of the column of water that the atmospheric pressure at point B can sustain. Now let me talk about the and of course, if this had been oil, you just divide it by 920 multiplied by 0.76 to tell you the height of the column of oil that this pressure can actually sustain. Now we go to let me talk about we're going to leave this for a while. So let me talk about the manometer quickly. There are 9 instruments used for measuring. I'm talking about the U2 now. U2 manometer. And how does this work? Pretty straightforward. You have a U-shaped container like so. This is a U-shaped container like so. Alright? U-shaped container like so. And this end is exposed to the atmosphere. Now, but the other end is connected to a gas whose pressure I'm interested in knowing. So let's say this is okay. So now I drop a fluid here. Let's say, for instance, let me take for instance that this is mercury. And right here, because this spot is exposed to the atmosphere, so the pressure right here, the atmospheric pressure here is exactly 1 atmosphere. 1 atmosphere. Now, if the pressure of the gas and the pressure here were equal, what you see that this level must be the same as this level. That is a necessary condition. If I call this point A, I call this point B, this level has to be equal. So it means the pressure of the gas is pressure of the gas exceeds the atmospheric pressure, this level will drop, down the bit, and of course this level will go, right? And it will define this height difference as h. So if the pressure of the gas exceeds the atmospheric pressure, it turns out to be that the pressure of the gas will be the atmospheric pressure plus the difference in pressure between these heights, which I call delta P. And delta P itself is density of the fluid times G times H. But what if the density, I want to clean this up, but what if the density of the gas is less than the atmospheric pressure? What you see is that this level will go down, the pressure here is more, and this level will go. So it turns out to be that the pressure of the gas must be equal to the atmospheric pressure plus the change in pressure now, which will take a negative value. Why? Because delta P in this case should be density of the fluid times G times H, but G has to be a minus, so we get a minus value for it. So this should be P minus delta P. Now, let me just do one working example. Let's say, take for instance, that the pressure of the gas, for instance, let's say is more than the atmospheric pressure. So let me say, let this level, pressure of the gas, yeah. Okay. So let this level from here to here, let's say I have a scale, and that scale is in millimeter. So this is mercury. So let this level be 138.6 millimeter. That's this level from the top here. And let this interval here be, let's say 108, or let's say 103 points, let's say 5 millimeter. What will the pressure of the gas indicate? Pretty straightforward. Now, since the pressure of the gas is way more, this is depressed, this is elevated. So it turns out to be, I'm going to leave this for a while, like this one, like this one. So it turns out to be that the pressure of the gas has to be the atmospheric pressure plus this interval here. And this interval here has to be the total interval minus this interval. It has to be this minus this gives you this interval. So this H, the column, has to be 138.6 minus 103.5. And this is 1, this is 5, this is 3. So this is exactly, so this column is 35.1 millimeter. And of course it's of mercury. So this is exactly so delta P here, it turns out to be, see this is already in limit of mercury, this is 35.1 millimeter of mercury. And clearly, what's the atmospheric pressure in millimeter of mercury is exactly 760. So this is 760 millimeter of mercury. So when you sum the two up, it tells you what's the pressure of the gas is. So just to stick in the numbers, this is 720, 760 rather, plus 35.1. And that is exactly 795.1. So you get 795. So the pressure of the gas, will be 795.1 millimeter of mercury. And of course, you can convert this to Pascal. So thank you. Now let me just say one more thing about gauge pressure, just briefly. Now what's gauge pressure? If you have a tire like so, let's say this is a tire, and let's say the tire is actually deflated, it has collapsed. pressure that is simply a pressure that tells you the amount by which the pressure inside the tire differ from the atmospheric pressure. So gauge pressure